In this example, we're using the results of an experiment to determine a chemical formula. A chemist takes an unknown compound and decomposes it into 12.00 grams of carbon and 4.04 grams of hydrogen. Alright, those are the only elements that result from the decomposition. So this already tells us something. There are only two elements in this compound, carbon and hydrogen. So even though I don't know the chemical formula, I can represent it. I can represent it as CXHY. After all, the chemical has only carbon and hydrogen in it. There will be a certain number of carbon atoms, that's X, and a certain number of hydrogen atoms, that's Y. So that's a representation of the chemical formula. Well, that's nice, but it's far from an answer. We need to figure out what X and Y are. How are we going to do that? Well, think about this for a minute. This is a decomposition reaction. We know what a decomposition reaction does. It takes the compound and produces its elements. So in this case, CXHY decomposes into carbon, that's C, and hydrogen. Now hydrogen's a homonuclear diatomic, so it's not H, it's H2. Alright, so here's a chemical equation for this decomposition reaction. How does that help? Well, think about it. The chemist gave us grams of carbon and grams of hydrogen. I can convert those to moles. Where do moles go in a chemical equation? They're the coefficients. So if I convert grams to moles, I'll essentially get the coefficients that go with C and H2 in the products of the reaction. Let me show you how that works. The chemist's reaction produced 12.00 grams of carbon. I can convert that to moles if I look at the periodic chart. The entry for carbon on the periodic chart tells me that the mass of carbon is 12.0 AMUs. That also tells me that 1 mole of carbon is equal to 12.0 grams of carbon. That's our conversion relationship between grams and moles. So I take my grams of carbon, put it over 1, and multiply by the conversion relationship with grams of carbon on the bottom so that they cancel. And we find out that the chemist produced 1.00 mole of carbon. Alright, now we do the same thing for hydrogen. The chemist produced 4.04 grams of hydrogen. The entry on the periodic chart tells me that a hydrogen atom has a mass of 1.01. We're not dealing with hydrogen atoms in the equation, though. We're dealing with hydrogen molecules because hydrogen's a homonuclear diatomic. So the mass of H2 is 2 times 1.01, or 2.02 AMUs. That tells me that 1 mole of H2 is equal to 2.02 grams of H2. That's our conversion relationship between moles and grams. So now I can convert 4.04 grams of H2 times the conversion relationship, putting grams on the bottom so that they will cancel, gives me 2.00 moles of H2. Now what does all this tell us? It tells us that when CXHY decomposes, it makes 1 mole of carbon and 2 moles of H2. Well, where do those moles go in a chemical equation? They're the stoichiometric coefficients in the chemical equation. So I can actually put them in the equation. Now remember, numbers in a chemical equation are exact, so 1.00 wouldn't make sense in a chemical equation, so I'm just going to get rid of that 0.00 and call it 1. In the same way, 2.00 wouldn't make sense in a chemical equation, so I'm going to get rid of that 0.00 and just call it 2. So in the end, the chemical equation becomes CXHY decomposes into 1 C and 2 H2s, because I produced 1 mole of C and 2 moles of H2. Now do you see how this can help us determine the chemical formula of the compound? There's only one way this equation will balance, and that's if X equals 1. I've got 1 carbon on the product side, so I can only have 1 carbon on the reactant side. So X must equal 1. In the same way, the only way this equation will balance is if Y equals 4. After all, I got 4 hydrogens on the product side, so I can only have 4 hydrogens on the reactant side. So in the end, the chemical formula of this compound must be CH4, because that's the only way this equation will balance. Now let me make it clear what I did not do. I did not change subscripts in this chemical equation. I'm not allowed to do that. You can't touch subscripts in a chemical equation. However, X represented something. What I did was I found out what X represented. It represented 1. Y represented something. I figured out what it represented. It represented 4. So I did not change subscripts here. I only figured out what the subscripts represented. That's an important point to keep in mind. I can't play with the subscripts, but I can figure out what they mean.